This video discusses the imaginary zeros theorem. This theorem states if a polynomial p of x has real coefficients, and if a plus bi, where b is not equal to 0, is a zero of p of x, then a minus bi is also a zero of p of x. That is, if a zero is a complex number, then another zero is its complex conjugate. This theorem is sometimes called the conjugate pairs theorem because imaginary zeros always come in pairs. Now, this part of the definition that said b is not equal to 0, that was just stated because if b is 0, then the I falls out of a plus bi, and we no longer have an imaginary zero. To help this theorem make sense for you, think about when you had gotten an imaginary zero. Remember that a zero is just the solution to an equation when it's set equal to 0. So what kind of equations were we solving anytime we've gotten imaginary solutions? Well, quadratic equations. And then think about the techniques we used for solving quadratic equations that gave us imaginary solutions. We never got any imaginary solutions when we solved by factoring. Completing the square is just a technique we use to set an equation up for square root property, so that leaves us with quadratic formula and square root property. Those two techniques have something in common. They both have a square root in their solving process. So for square root property, remember x is equal to plus or minus the square root of a, and then with our quadratic formula, these were the only techniques that we used to get an imaginary solution, and that was because they had square roots. Imaginary numbers show up when we have negatives under square roots. Okay, notice that both of these techniques have a plus or minus in them. So we always got two solutions. The imaginary portion of the number comes from the square root, so that's after the plus or minus. And then sometimes we had a real number in front of the plus or minus. Well, those are the two answers. We'd end up with something like 2 plus or minus the square root of 3. We'll put a negative in there, so that gives us an I. There were two solutions, 2 plus I square root of 3 and 2 minus I square root of 3. So there's the a plus b and the a minus b. Every time we get an imaginary or a complex solution, there's going to be a plus and a minus. Hopefully that makes the theorem make a little more sense. All right, now let's use that theorem. We want to find the zeros of p of x equals x to the fourth minus 3x cubed plus 6x squared minus 12x plus 8, given that x minus 2i is a factor. We're trying to find all the zeros of p of x. The way that we find zeros is by setting it equal to 0, factoring the polynomial, and then setting our factors equal to 0. So basically, we need to get p of x in factored form. We've been given one of the factors. Notice that it has an imaginary number in it. So we have the factor x minus 2i. From every factor, we can obtain a 0. We get the 0 by setting our factor equal to 0 and solving. So the factor x minus 2i gives us the 0 x equals 2i. Our imaginary zeros theorem says that every imaginary zero is going to have a partner with it, its complex conjugate. Now this 0, 2i is not written in true complex form. True complex form is a plus bi. We can rewrite it that way though. This is the same as x equals 0 plus 2i, and now it's in true complex form. Our theorem says if a plus bi is a 0, then we know that a minus bi is also a 0. Therefore, x equal to 0 minus 2i is also a 0. Now I'm just kind of going to work backwards from right to left with this little chart I've made to get another factor. This can simplify to just a 0 of x equals negative 2i. I want to get the factor that goes along with this 0 because ultimately I'm trying to factor p of x. I get that factor by setting my 0 equal to 0. So adding 2i to both sides, we get x plus 2i equals 0. That makes a second factor x plus 2i. Since we have two factors, we can start factoring our p of x. P of x is going to be equal to x minus 2i, x plus 2i, and then we're going to have another factor. That factor is going to be quadratic because we started with a fourth degree and we've already found two linear factors, so 4 minus 1 minus 1. Our next factor is going to be quadratic. All right, well, how do we get this other factor? Consider knowing that the number 48 is equal to 2 times 3 times some other number. That's essentially what we have right now. How would we figure out what the third factor of 48 is now that we know that 2 and 3 are factors? There's two options. We could either divide 48 by 2 and then that answer by 3 to get the last factor, or we could multiply the 2 and the 3 together, get 6, divide 48 by 6 to get the third factor. Since you don't know how to divide by imaginary numbers, we're going to want to choose the second option, where we multiply the 2 and the 3 together and then divide 48 by 6. So to get the third factor, we're going to multiply x minus 2i and x plus 2i together. Then we're going to divide our original p of x by the product from step 1. All right, let's do that. First, I'm going to multiply these two factors together. That'll be x squared plus 2xi minus 2xi minus 4i squared. We have like terms here in the middle that we can combine, but notice they cancel out when we combine them. We also have an I squared. Recall that I squared is equal to negative 1, so really we have negative 4 times negative 1 here. This product simplifies to x squared plus 4. Now we want to divide p of x by that x squared plus 4. Here's our original p of x. I want to divide it by x squared plus 4. Notice that our divisor is missing a linear term, so we want to be sure to put a placeholder in. That makes the divisor x squared plus 0x plus 4. And now we divide. X squared goes into x to the 4th, x squared times. Multiplying back by the entire divisor, we get x to the 4th plus 0x to the 3rd plus 4x squared. We'll subtract. Gives us negative 3x to the 3rd plus 2x squared minus 12x. Let's divide again. X squared goes into negative 3x to the 3rd minus 3x times. Multiplying back by our entire divisor, we get negative 3x to the 3rd plus 0x squared minus 12x. We subtract. X to the 3rd cancels out. We're left with 2x squared. Notice our x terms cancel out as well, but I'd like to keep a placeholder there since it's in the middle. So plus 0x plus 8. Dividing again, x squared goes into 2x squared, a positive 2 times. Multiplying back, 2x squared plus 0x plus 8. And we subtract again. Notice that all of our terms cancel out and we're left with a remainder of 0. This should not be a surprise that we have a remainder of 0. What we're finding is a factor, and we know that factors have remainders of zeros. All right, this x squared minus 3x plus 2, this is our third factor. Let's continue factoring p of x. P of x is going to be equal to our first two factors, x minus 2i and x plus 2i. And now our third factor is x squared minus 3x plus 2. To find the zeros, we want to get our p of x totally factored, and then we'll set each factor equal to 0. We can factor the quadratic factor, x minus 2 times x minus 1. Now that we're in factored form, we set each one of our factors equal to 0 and solve to get all of our zeros. Our list of zeros will be 2i, negative 2i, positive 2, and positive 1.